Dear students and participants of the course of Railway Engineering, we are back with our discussion. Today, we are going to discuss about the track stresses specifically in the rails. If you remember, in the previous lecture, we started already with the track stresses and we have discussed about the stresses which can be caused because of the vertical loads, and then we had a discussion on the dynamic augmentation of those vertical loads in terms of various reasons. Then lateral forces, longitudinal forces and the curve effects were looked at. Now in today's discussion, we are going to discuss about the bending stresses and the moments in the rails which are induced because of different reasons, again the type of loadings which can be there in terms of vertical loadings or the lateral loadings, and then the stresses which can be computed on the basis of that. Towards the end, we will be looking at one of the numerical and we will solve that and understand the whole procedure of working with the bending stresses and moments in the rails. So, let us start here. Now, we are discussing about a rail and the wheel interaction here. Now, when the wheel moves at the top of the rail as being shown on the right hand side, then this particular interaction is being considered in the form of the two cylinders which are going to interact with each other. Now, when we talk about these two cylinders, the axes of these two cylinders are going to be at right angles to each other. Say you are talking about the rail, so rail is moving here in this longitudinal direction. At the top of that, the wheel is going to move and this wheel is taking a rotation in this form and continuously will keep moving all along this particular rail. So, here one cylinder is being taken in this direction, another is being considered in the other direction. So, x and y coordinates maybe you can consider in that form. And the contact area which will be there at this point is an elliptical shape. So, through that contact area, the whole of the load which has come to this particular wheel from the axle, and that is where if an axle load is P, then the load on the wheel can be taken here as P by 2. So, that is going to be distributed through this elliptical area. Now, the maximum contact shear stress at the contact point between the wheel and the rail is given by equation F is equals to 4.13 multiplied with the under root of the ratio of P and R. Now, where P is the static wheel load and this static wheel load is being enhanced by 1000 kg or 1 tons for an on loading on the curves, and the R is the radius of the fully worn out wheel. So, this radius R we are talking here, but then in this case we are considering that this wheel is fully worn out. So, this is one formula which we have so as to calculate the contact stress when we have an interaction of rail and wheel. Now, this maximum value of the contact stress between the rail and wheel, it is being limited to 21.6 kg per mm square, and this 21.6 kg per mm square is correlated with the ultimate tensile strength of the rail section. Say if the ultimate tensile strength of the rail section here is 72 kg per mm square, then this limited value of the contact stress is 30% of the UTS. So, that is how this maximum value of the contact stress can be also calculated for other rail sections. The number of sleepers per rail have little effect on the stresses in the rail. So, whatever the sleepers have been provided at the bottom so as to take the load from the rail and distribute it to the ballast. So, here we discussed in terms of the track modulus, there it was contributing not only in terms of the type of a sleeper as well as the sleeper density, but in the case of these track stresses when we are talking at this point where the contact is there between the wheel and the rail section, it has a lesser effect. The another condition which may happen is the eccentric vertical loading. Now, when you talk about this eccentric vertical loading, if you see here the center line of the rail section is at this point. So, this is the center line and at this center line if the load acts as P or P by 2 whatever the value we consider here, there is a possibility that because of the interaction of the wheel with the rail head or the surface of the rail head and this lateral movement in either of the direction, the loading comes at some other point, as you can see in this diagram. This loading is coming at this point. So, this is Fv and it has gone at an eccentricity of E with respect to the center line of the rail section. So, this eccentricity is going to cause the bending moment along with the torsion of the beam. So, it will create a condition like this as well as it will try to bring in the torsion condition. Another condition is the lateral thrust. The lateral thrust at the rail head produces lateral deflection and twisting of the rail. So, from where the lateral thrust is coming? Now, if you are talking about this arrangement of a flange, so this is a flange on this side which is going a bit down like this. Now, as soon as this comes and hit the rail head, so there is a lateral thrust. So, this is a lateral thrust which is coming on the rail head, and this particular lateral thrust again is going to create the problem with respect to the connections of this rail with the sleeper, and it is creating an impact in this way. So, this is another case which needs to be taken into consideration, and it causes the lateral deflection in the sense that if it is coming from here. So, there will be some movement in this form. So, this is the deflection which will be there, and the lateral deflection also causes lateral movement of the sleepers on either side. So, if this lateral thrust is very heavy, then with respect to these fastenings which are there, there is a possibility of some movement in the sleeper too. Now, this contact shear stress under the repeated load conditions causes fatigue of the wheel thread and rails. So, if this same thing keeps going on, whatever the scenario which we have discussed here, if this keeps going on, then finally there is a possibility that there can be a fatigue on the surface of the rail head, which is a tabletop, also it is the name which is given to this, or there will be a problem in terms of the corner or the side of the rail head. So, that fatigue condition is another issue which will be there because of this contact shear stress. Now, very high stresses occurs in the lower fillets on sharp curves. Now, when we are talking about sharp curves, we have repeatedly discussed about it, and on this sharp curve the wheel is moving like this, and similarly here also it is moving in this form, and this movement is going in this way, where is the centrifugal force is acting outwards. So, there is a pressure, higher pressure coming on this side as well as there is a higher pressure coming on the inner side, depending on whether you are talking about the front or the rear axle condition. So, these higher stresses are also going to be there is on the curves, and the effect will basically come to the lower fillets. So, at a rail seat where we are talking. Another condition is that the temperature variations can be there. So, if there are temperature variations, so there is already a temperature at which the rail is being laid. So, if that temperature, say if we are talking about the mean temperature, or you are talking about the stress free temperature, we will be discussing about these temperatures a bit later when we take up LWR and the breathing lengths, etc. So, if this laying temperature is there of a rail, with respect to that the temperature in the air can goes up and can come down, and that will cause the expansion or contraction of the rail. And because of that expansion and contraction, there are going to be the tensile and the compressive stresses which are induced in the rail section. Now, tractive effort and braking force, these two things we have again discussed previously. So, when a rail section is provided in this way, as we talk about a rail, and there is a wheel which is moving at the top of it with some load coming here. Now, when you talk about the tractive effort, this tractive effort is going to work in this form, and therefore, there is a component here and the component downwards. So, this is a tractive effort which we have discussed previously. Another case can be that there is a braking force. So, when you apply the brakes, you are trying to stop it, and when trying to stop it, then this condition will be there. But then because of that, there is a issue of some force being exerted, and if you are on a joint here. So, this is say one rail and this is another rail on this side. So, if it comes here, the wheel is being positioned at this location and you apply the brake, then it is going to create a problem to this rail end. So, there are again going to be lot of stresses in this case, and the effect of this is going to be higher if this wheel diameter capital D is small. So, if this is a small value, what will happen? Whatever gap is being provided, it will not bridge easily, it will not jump on this particular joint, rather it will strike the rail head. So, this rail head at the end is going to be battered. So, there is a possibility that it will slowly and slowly will start taking a shape in this form. Then track irregularities, they also causes the heavy impact and the deflection, because if the track is uneven, so it means the rail level, if it is goes in this form, because the irregularities are there at the formation level. So, this is formation and this is rail level, then in that case also there will be the stresses. Now, let us talk about the bending stress in rails due to the vertical load. Now, here the assumption is that the rail is a long bar continuously supported by an elastic foundation. So, the rail is being supported by sleepers, it is further being supported by ballast cushion on the formation level. So, what we are considering here is everything is elastic in nature, therefore, whatever loads comes at the top and deflection may be there, but as soon as the load is removed, the deflection will also get removed. Now, due to these vertical loads, the rail is subjected to bending and fractural stresses. So, these are the two type of stresses which are going to be there, and this is what we are calculating now. So, based on the elastic theory, the bending moment can be computed by using an equation m is equals to 0.25 into p into L into exponential of minus x divided by L. So, that is a ratio which we are considering, and the whole is being multiplied with the sine of x by L minus cos of x by L. So, this is the equation which can also be used so as to compute the value of the bending moment. Now, here what are the various parameters which are being used? Let's look at that. So, P is isolated vertical load. Continuously we are talking about P in that form, and if it is a small p, we talk in terms of pressure. Then L is the characteristic length, and it can be calculated by using a formula which is the fourth root of 4 EI divided by U, where E and I, they are the modulus of elasticity and the moment of inertia, but together E and I can also be defined as the fractional stiffness of the rail section, and this U is the track modulus. We discussed about the track modulus as the initial track modulus and the elastic track modulus. So, it means these are the two things which will be there, initial and elastic, and in the case of initial for broad gauge, this load was taken as 4 tons. So, therefore, for the elastic condition, if we are talking about a broad gauge, whatever is the total load which is coming, say as P. So, for elastic load computation, this is going to be P minus 4 value. And x here, it is the distance of the point under consideration from the load. So, wherever the load is applied, so load is coming through the wheel. So, wherever is the location of the wheel is there on the rail head. With respect to that, at what particular point we are computing, so that x has to be taken in that form. And in this direction, if you remember, we did talk about the relief of stresses. We had a diagram where a effect of a single wheel inducing positive bending moment and a negative bending moment was discussed, and then we talked about the two successive wheels, and then because of that the reduction in the positive bending moment, because some of the negative bending moment will come into that area subjective, the two wheels are nearer. So, that effect is also being taken up. And when we will taking that particular effect, you will see that when you go into the numerical side, then you will be understanding that how that is being taken. Now, this is the same diagram which we have discussed in the case of that relief of stress. So, here is the maximum bending moment which is getting generated below the load being applied with respect to the wheel location on the rail, and then at some distance away from that location of this, there is a point of contraflexion, and then the sign changes. So, the compression changes to tension conditions, but again this is going to be higher at some location, and then finally it will start reducing with respect to the length of the track, or here the length of the rail. Now, this bending moment maximum value is going to be this one, that is PL by 4, whereas the bending stresses is nothing but it is the bending moment divided by the sectional modulus of the rail, and this sectional modulus of the rail has to be considered with respect to compressive or tensile zone. So, in the rail section there will be a neutral axis. With respect to neutral axis, at one side there will be compression condition, on the other side it will be tensile condition. So, we need to calculate the sectional modulus of that section only. So, the bending moment is going to be 0 at point x is equals to pi L by 4, 3 pi L by 4, and it is going to be maximum at x is equals to 0 or pi L by 2, 3 pi L by 2, etc. So, this is how the successive values will be there. Now, the bending moment, one of the formula we have seen. Now, the another formula which can be considered or used is 0.319 into P into x, where P again is an isolated wheel load in tons and x is the distance of the load from the point of contraflexion, and this distance is calculated using an equation 42.3 and the fourth root of I by u, where u is the subgrade modulus and I is the moment of inertia of the rail section. So, if these two values are known to you, then we can calculate the value of x, and then we put the value of x, P is already known to us. So, that will give us the maximum bending moment. So, this is another way of doing it. Now, let us look at this figure which is being taken from Railway Track Engineering by J.S. Bondre, and this is being created for a locomotive defined as 462 locomotive. We have also discussed about these nomenclatures previously. The permissible speed is given as 72 kilometers per hour. So, for this 72 kilometers per hour speed, the bending moment and the deflections has been looked at. So, here 462 means this is a 2 axles and 4 wheels will be there, this is 3. So, there are 6 wheels conditions, likewise this is being provided, and these are the distances between the wheels. So, distance between wheels. So, like if you see the first two, they are at 187.8 value, then another one are 94.5, then 150.4 and so on. All of these values are there. Now, in terms of the bending moment, you can see that there is going to be an impact of one particular wheel, and that will create a positive and negative, as we have already seen previously here. So, the same conditions are happening, the only thing is they may be reversed in a value. So, the maximum value is attaining here below this load, and then at some distance away you found that there is another change, the change of the nomenclature or the sign is there. So, there is a compression or tensile conditions being created. And here one another thing which can be looked at is that there is a static load being defined here, and then there is a live wheel load which is actually the augmented value of those static load, depending on that what are the conditions, what are the speeds which have been given here. Similarly, the track depressions are being shown. You can see that these are the 3 bigger wheels and the load through these particular wheels is going to be heavy, and that is the reason the deflection is higher in this range as compared to the other ranges. Now, if you have to calculate the bending stress, we already have the maximum bending moment value with us. So, this is nothing but that bending moment divided by Z, and then this F if we put the value of m here, it becomes then 13.5 into p into I over u and the fourth root of that divided by z. Now, m is obviously we have calculated this value, this is the maximum bending moment. So, it is a centimeter tons. F is the stress in the rail head which is caused due to the bending moment immediately under the load P, and the permissible value of this load is 22 to 25 kg per mm square. And the Z value is the modulus of rail section, and this modulus of rail section has to be taken either in tension or compression. So, depending on that which particular side we are calculating the value of this F. So, this F will again it will be either in compression or in tension. So, this value will define accordingly. So, we are not giving all those values here, we are simply understanding the concept behind this. Now, the deflection due to the vertical load, this deflection due to the vertical load is computed by the formula 9.25 into W divided by I u cube and the fourth root of that, where D is the deflection of the track, W is the isolated wheel load, U is the modulus of track and is the moment of inertia of the rail section. So, this is giving you the values which are being shown here and this point. Now, one another thing is the reduction factors are used. Now, these reduction factors, they are used with respect to the distance of the wheels, that is what is the distance between the two wheels. So, the rail section we have, and this is one wheel and then this is another wheel. So, what is this distance at which they are being placed? And another point is the distance from the point of contrafracture which is calculated. Now, once you have these two values, then what we do is that suppose it is a value of 150 and this distance from the point of contrafracture is 75. So, we will go along the curve to 75 and then from that 75 we will go vertically upwards like this, and then we will see where this particular line intersects the two curves given at the top. The one curve is the reduction factor for the bending moment, another one is for the deflection. So, if we talk about the bending moment, so the lower one is for bending moment, here the value comes out to be roughly around minus 0.2, a bit more than that. So, we can take as an extremity of 0.2, so that value can be considered. And then if we go for the deflection, then in that case it comes out around 0.2 positive side. So, it has a sign also minus or plus. So, that value we will be considering whatever the deflections or whatever the bending moments are there, they are going to be modified on the basis of these. This lift of rails we did talk about previously, just look at quickly on this. This is a wave like effect gets created in the rails with the passage of train. The this wave like effect we have understood because it is an elastic medium, wherever the load is coming, deflection is there and the rail gets lifted in the front side, and it may happen because there is a loosening between the rail and the sleeper, but if they are tightened, then it also creates a stress, negative stress is getting created there, and this is what we have already talked about. The rail tend to bend upwards at some distance ahead of the leading wheel, and usually there is a play between the rail foot and the dog spice, and it tries to keep it to permit the lift of the rail up to a certain value only, and it causes an increase in the bending stresses which is by 10%. So, this lift of the rail is going to be considered, and wherever that effect will be there with respect to the value of x which we have calculated a point of contrafracture, the 10% increase is going to be made in the values. Now, when the condition of the sleeper is poor, then the increase in the stress may exceed this value, but then for that experimental work needs to be done. So, at that time also we said that this condition arises when all axles are spaced at a distance greater than 6x, where x was the distance of the load to the point of contrafracture on the rail. And this x is calculated as we have discussed in the previous one of the slide is 42.33 multiplied by the fourth root of a ratio of I and u. So, once we have these values, then moment of inertia of rail is reduced by 10% to cater the load loss of section of the rail in service. If there is a problem with the rails, they are not being maintained, the section has reduced, then in that case instead of increase which we have talked previously, there will be a reduction of 10%. So, now let us come to a numerical here. It says calculate the stresses caused in the rails due to WDM2, a broad gauge diesel locomotive with axle load and driving wheels at 18.8 tons running at a speed of 105 kilometers per hour on a 90-hour rail, which is placed with a sleeper density of M plus 4 on 200 ballast cushion. And the data with respect to the spacing of the wheels is being given. The first wheel and the second wheel, they are at a distance of 170.2 centimeters. The second and third, they are at 210.8 centimeters. And then this one set is being put at a certain distance away, which is 521.4 centimeters, with the another set of 4, 5 and 6, and again the distances are same with respect to 6 and 5 and 5 and 4. So, let us solve this. Now, in this case, as we talked about the track modulus, we have to consider the initial track modulus as well as the elastic track modulus. The initial track modulus is 78 kg per centimeter square for the given conditions, and for that the initial load is 4 tons. But if we talk about the elastic track modulus, which is beyond 4 tons, the value is 300 kg per centimeter square. And assuming that there is a 5% wear on the rail section, the I and Z, they are being calculated and then further being reduced by 10%, as we discussed. If there is a wear on the section, then the values has to be reduced by 10%. So, considering that, let us have I in the x direction as 1440 centimeter 4 and the ZC, that is compressive condition or the tensile condition, the worn out condition, it comes out to be 192.46 and 212.08 centimeter cube. So, these are the values. Let us assume that we have got on the basis of the calculation for the section of 90R. Now, this x for the initial load of 4 tons, the equation was 42.33 multiplied with the fourth root of I over u. So, I here is 1440 and u, if you are talking about initial, then it will be 75. If you are talking about elastic, then it is 300. So, if we consider that if it is 75 or it is 300, we will get two values now. One is for elastic initial load, another one is the elastic load. So, it is 88.61 and this comes out to be 62.66. Now, the actual load which is given is 18.8 tons. So, the wheel load is half of that. So, we have 9.4 tons with us. And with respect to the speed at 105 kilometers per hour, the speed factor can be found out. So, there are graphs been given in the Indian Railways guidelines. So, from there say it comes out to be 41.5%. So, it means whatever the load is here, the wheel load which is here as 9.4 tons, it is going to be augmented. That is what is the speed factor. So, it is multiplied with a factor of 1.415 or an increase of 41.5%, and that gives a value of 13.301, or let us take it as 13.3 tons. So, this is a live wheel load adjusted value which we have now. Now, coming to the bending moment coefficients from the reduction factor graph which we discussed previously, and this is the graph being shown again here. Now, we have two values of x, one is 88.61, another one is 62.66, and there are distances between the wheels. So, the first distance between 1 and 2 was 170.2, for 2 and 3 this was for 1 and 2, this was for 2 and 3, and if we add these two 170 and 210, then this becomes a distance between 1 and 3. And then 521.4, this 521.4, if you go back, this is the distance between 3 and 4. And if you consider it with respect to 1, 4 or 2, 4, then also the value is going to be higher. Now, once we have got these distances or the interactions of the different wheels which we have identified here, this is wheel interaction, and the factor which needs to be considered for that interaction is what we are talking here. So, for say a value of these values, the set here which is given, this is for 88.61, whereas the set other side which is given is for 62.66 centimeter load for different distances. So, if you are talking about say 170, so 170 is somewhere here, and for that if we go ahead for a value of say 62.66. So, if we are going with the 170 along this for 62.66, it will be somewhere here, and then if we go straight up very near to this vertical line. So, we are coming at some point up. Okay. So, when we come at that point, it may give you a value of say negative of 0.15. So, likewise all these factors have been identified. So, these are the reduction factors which we are going to consider further. So, here we are adjusting those live load or the wheel loads which are there with respect to the initial load of 4 tons and the elastic load which is the augmented load minus 4, that is 9.3 tons. So, the one value is being done for 4 and one is being done for 9.3. So, if you are talking about load 1, so there is no interaction, there is a wheel here, the first wheel is there, number 1. So, whatever load is coming here, that is going to be considered as such. Now, when we talk this 1 and 2, so this is 2, the load is coming at that 2 also, but then these 2 are at a distance of around 170 centimeters. So, 1 and 2, if we go back for 1 and 2, for 170 centimeters, the factor is minus 0.2. So, that minus 0.2 has been considered here with 4 and we get a value of minus 0.8 tons. Similarly, if you are talking about say 2 and 3, the 2 and 3 means the distance between 2 and 3 is 210 and the factor is minus 0.19. So, minus 0.19 into 4. So, you get minus 0.76 tons, and similarly in the case of 1 3. So, 1 3 is here, it is 0.02 negative. So, this 0.02 negative is being taken with 4 for 1 3 and what we get is minus 0.08. So, if we take rest of the combinations, the values are going to be 0 because now we are going to higher values here. The same thing is being done on the elastic side also, and there the initial load augmented is 9.3 and then with respect to the factors we get these values. So, we have now changed the values of the live loads. Now, the effect of wheel load is to be taken if the distance between the adjacent axles is more than 6x. So, x we have calculated, x is here this is 88.61 and this is 62.66. These are the two values. So, 6 times of this. So, if we take 6 times, this is roughly 90. So, around 540 and in this case it is 60. So, it is a bit more than 360. So, what we get is 531.66 centimeters and 575.96 centimeters for the initial loading and the elastic loading conditions. It means if the wheels are so much distance apart, then only the effect of those will be considered, means 1:2 or 1:3 or 1:4, 1:5, 1:6, that is what we are discussing here. Another thing is, in the case of initial loading, only wheel 1 and 6 effect is being taken with respect to the leading axles. So, this is for initial loading condition. In the case of elastic loading conditions, what will happen because of these distances, because here if you see the elastic load condition, the distance is 375.96. If I go back, so 375.96 here, now 3 and 4, the distance is greater than 375.96 centimeter. So, because of that, this interaction will also come into play. So, once we have identified that which are the wheels which are going to interact and therefore, the values are going to change. So, let us move forward. So, this is a table for the initial load of 4 tons. So, here in this case the 1:1, if we talk, this is 1 and this is 1. So, 4 tons will be there. If we are talking about 2 and 1, so we go back 2 and 1, this is minus 0.8. So, minus 0.8 here, then 3 and 1. So, 3 and 1, this one is minus 0.08. So, minus 0.08. So, if we talk about say 2 and 2 it will remain 4, but if it is 2 and 1, so 1 and 2 condition will repeat here. So, these 2 will be same, and if we talk about here for 3 2, then it is 2 3 2. Let us move back and see 3 2 is 2 3 is 0.76 negative. So, it is 0.76 negative. So, likewise all of this table can be created, and then at the end what we have is a virtual wheel load. This is a Telvoid impact value condition. This is nothing but a summation value. So, 4 minus 0.8 minus 0.08. So, that is where the relief is coming into picture. So, relief of stress which we have discussed, that impact we have considered now here. So, we have the values as 3.12, 2.44, 3.16, and then there is again a repetition of those values on the other side. And a similar analysis is being done for the elastic load, which is 9. I think it's 9.3 tons. So, you can make that change here. So, it is 9.3 tons. Accordingly, some of the values will change in this particular table. Kindly do that by yourself. So, and here again for these particular values, you go back, you have the values available here 9.25 and 9.3. They are not making much difference in terms of the computation. So, these values are not changing, only a one more factor after 2 decimals may come. So, if you talk about for elastic interaction is 1 and 2. So, it should be 1.39 and 2 and 3.74. So, 1 and 2 is here you are talking 1.39 negative, and then 0.74 is for 2 3. So, likewise again these values are being placed and then summation is being done at the bottom. So, we have got 2 sets now. Now, the another thing is the virtual wheel load. With respect to the initial load of 4 tons, here the 6x value is 531.66. Therefore, there is only an impact between 1 and 6, and this impact is going to be increased by 10%, and that is where the value of 3.12. So, this is 3.12 between 1 and 6. So, this 3.12 has been increased by 10%. We got 3.432. Similarly, when you talk about the elastic load, so there we got 2 conditions. One is for 1 and 6, but another one which we identified additionally was 3 and 4. So, for 1 and 6 the value is 7.86. So, this 7.86 has been increased by 10%, and in the case of 3 4 the value is 8.51. So, this 8.51 again is being increased by 10%, and we have got these 2 values. So, once we have got these values, now let us move into the combinations here. So, combinations for the elastic load and for the initial load and the elastic load are being shown here. So, the enhanced value is here as well as here. Similarly, for elastic load, this is also an enhanced value, and this one is also enhanced value, and finally, these 2 values are the enhanced one by 10%. So, once we got these, then we take again a summation here to see what is the worst condition, and the worst condition comes out to be 12.521 below the wheel 3 and 4. So, this is 12.521 tons is the maximum TIV, and once we have got this maximum TIV, then the bending moment in the rail is being calculated. So, we have a value of these 0.318 into 3.16 into the x value and 9.361 into the x value. So, this is the total bending moment which comes here. Now, once you have got the bending moment, and if you have the Z values available to you or the compression and tension, so considering those Z values, what we can get is the F in compression and F in tension. Now, with respect to these values of F in compression and tension, one thing is given, the permissible values is 23.5 kg per mm square for all rail steel, and the maximum ultimate tensile strength of rail steel varies between 70 to 85 kg per mm square with an average of 77 kg. So, this is a rider. So, on the basis of that, we can check that whether what we are getting is permissible within permissible conditions or not. So, with this we close our discussion here on the bending moment. What we discussed about the track stresses which are getting induced in terms of bending stresses or the bending moments due to different vertical load conditions, and then we computed those stresses in the rail head and the foot. Thank you. We will be meeting again.